Okay, off we go. So last time we were talking about the chain rule, and let me just remind you of the very broad strokes, the big idea of the chain rule is to recognize that what a derivative does is find a relationship between input velocity and output velocity. That's one way to think about it. It's a multiplicative factor that you apply to the input velocity to get the output velocity. And then, well, you can think of this process of turning this initial input velocity into this eventual sort of final output velocity as just a succession of applying the derivative of f, and then to that result we apply the derivative of g. Right? And if you turn x prime into y prime and y prime into z prime, all together as a whole, what you've done is you've turned x prime into z prime by the multiplication by this product of two matrices. That product matrix is the matrix that turns x prime into z prime. So that's the broad strokes, big picture there. And let's see here. So we talked about the details last time. And reminder also, the pithy sort of phrasing that describes it is that differentiation turns a composition, right, into a product. And this is, of course, a matrix product. Okay, so let's see an example of this in action. I think that's where we left off last time. And let's see here. I'm going to zoom in for a little bit more space. We've got a couple of functions given here. Notice that I have the outputs from f are the same as the inputs to g. Right? And that had better be the case because, after all, we're composing these two functions where, again, f acts first, so the output from f is going to be, had better be, the same as the inputs for g. Okay. So, with all this set up, how am I going to use this information that's given to find the derivative matrix of the composition at the point 1, 2? Okay, well, here's the chain rule from the previous page applied to the situation at hand. Derivative of g compose f is dg times df. Evaluated appropriately, of course. Now notice I want the composition evaluated at 1, 2, so I better have df evaluated at 1, 2, and good news, I am given df. Where was I going? I am given df evaluated at 1, 2. So that is just this right here. Now we got to be careful about this next one. I need dg evaluated at f of 1, 2. Problem. What is f of 1, 2? Well, thankfully, that's given. F of 1, 2 is 3, 1, 0. So what I really need is dg evaluated at 3, 1, 0. And thankfully, that too is given. And so, as we would probably have expected, finding this derivative of a composition is just a matter of taking the product of these two given derivative matrices and a little matrix multiplication, and there you go. And there's our DG matrix, derivative of the composition matrix. Is everybody happy? Do notice one thing, and by the way, in the coin flip reality of the world, about half the time that you have a question like this, where you have given matrices, about half the time they're going to be written in the wrong order. Right? If they're written in a random order, like I did here, well, it's a coin flip. So notice in this case, the one that applies first, namely the one that's on the right, happened to be given on the left. And the one that applies second, namely the one that should be on the left, was given on the right. So there's a kind of a little switcheroo in terms of the order that's necessary in this application. I did it on purpose in this example. Purpose of which is that, again, the real world will do this half the time, so you need to be ready for it. So, again, please don't think in terms of left and right, which one's on the left, which one's on the right. Think in terms of which one acts first. And always interpret appropriately whether you're looking at matrices that are multiplying by each other or whether you're looking at functions that are being composed with each other in this little algebraic notation, or whether you're looking at a diagram where where it goes, left to right instead of right to left. And always think in terms of first and second, not left and right. Okay, now there's a second part to this question. Second part of the question is to compute this specific partial derivative, partial of z3 with respect to x1. Okay, this is a partial in the composition. It's an element of this matrix that we just computed. Keep in mind, this composition takes the x's to the z's. And I am going to zoom out so we can see a little bit more all at once here. Okay, so let's keep track of what's where. We are asked apparently to compute the partial with respect to x1. Where is x1 on this picture? Well, it's the first input variable. Remember, input variables correspond to columns. So if I say I want to take the partial with respect to the first input variable, I'm going to be looking for an entry in this matrix in the first column. Which one? TBD. But I know that what I'm looking for is in that first column. Yeah? Okay. Next, apparently, I want the partial of z3 with respect to x1. z3 is the third output variable. And being as it's the third output variable, a partial of z3 will be in the third row of this derivative matrix that I just computed. So altogether then, I'm looking for the entry that is in the first column, third row, and that is this number right here, and that then is the answer to this second part of the question. How are we doing? Yes?
So it's not the partial because that's what the Jacobian matrix is.
Yeah, that's right. Jacobian matrices are, all of the elements of Jacobian matrices are individual coordinate partial derivatives. Yep. All right. Okay. So, all right, let's take a different point of view now on the chain rule, and this will come out of what we've just done. I got ahead of myself. I'm sorry. I need to talk about some special cases. I'm going to be really quick with this because these special cases, there's in some sense nothing new here. I just kind of like to connect dots when there's dots to be connected, and so let's entertain momentarily the question of what happens if there is a single initial input variable, right? So the first function is a function of just, let's say, t. Okay, well, what happens there? Well, let's look at this first function. This first function gives position as a function of time. That's a parametric curve. Let's look at the composition. The composition gives position in the y space, if you will, as a function of time. Again, that's a parametric curve. Right? So, furthermore, notice, because there's only one input variable, the derivative matrices for these two functions, derivative matrix for the first function, the derivative matrix for the composition functions, one input variable means one column, because columns correspond to input variables. So, okay, well, we've got a parametric curve in the x space. We've got a parametric curve in the y space. Right? These derivative matrices are single column. They're just the velocity vectors of those parametric curves. And this gives us, I'm going to say it recovers for us, something we already knew about the derivative matrix of f. The derivative matrix of f is a matrix that relates input velocity to output velocity. We already knew this. Right? This is one of our initial interpretations of the derivative matrix. So what's kind of cool about this is that we can now interpret that as being sort of a special case of the chain rule, if you choose to think of it that way. So, anyway, some people like to think of it this way. Whatever. It's all good. And a quick example, and I'm going to be real quick with this because, as usual, we're behind schedule, tough choices, and all that. But this is an example that very well could have been a couple of sections back when we first defined derivative matrices. We have here a function, two input variables, three output variables, and I've got an input velocity. There it is. Our input velocity is 4.3, and the question asks us to compute the output velocity, df dt, whatever that is. How am I going to compute that output velocity? Well, per the result on the previous page, that output velocity is the derivative matrix that I can compute by taking partials and plugging in the appropriate point. It's the derivative matrix times the input velocity. And you can multiply that all out. And there you go. It's just derivative matrix times input velocity gives you output velocity. Again, this could have been 2 sections back. But we're just going to introduce it here. Reintroduce it here as a special case of the chain rule. Okay, next special case. This is a special case of a special case. Reminder, we've already talked about what the consequence is of having a single initial input variable. That means that we're going to have a single column there, and of course we're going to have a single column there. Now I'm going to add a further condition. The special case of this special case is suppose I have a single eventual output variable. Output variables, of course, correspond to rows. That means that the composition only has one row, in addition to only having one column. And it means that this f function here, its derivative matrix also has just one row. All right, so combining that all together, the composition is just a single real number. It's just a calc 1 derivative, dy dt. The derivative matrix is a single row matrix, and the what I have on the right here is again an input velocity. So, reminder, when you're multiplying a matrix times a vector, if there's just a single row in that matrix, it is computationally identical to doing a dot product with, sort of turn that row sideways to make it a vector and, do a dot product. So, and of course, if you turn that matrix sideways, it's just the gradient. It's the vector of all partial derivatives. So, again, old fact. We've seen this before, right? We talked about this a couple sections back. But, again, you can choose now to view this as a special case of the chain rule. So, again, application. Again, we could have done this 2 sections back, so I'll be quick. But here is a function. Temperature is a function of position, such as, for example, in this room. I'd be willing to speculate it's probably warmer over there by the windows, and it's probably cooler, back here in this corner where there's shade and, stuff like that. So, suppose that's we've got this function giving us temperature as a function of position. And suppose I'm moving with an input velocity. What is the rate of change of the output? And per the formula on the previous page, the rate of change of the output is going to be a dot product of the gradient and that input velocity. And again, just multiply it out. Answer, yes.
What is little t referring to?
Little t here I'm interpreting as time. So I've got a bird flying around here, right? And the bird is flying in such a way that its position changes with time, and that means that the temperature at wherever it is also changing with time. So the little t here is time.
So is the velocity statement like 2 over t, like 0 over t, 1 over t, or does it not get expressed like that?
Well, no, the velocity is just a vector. There's units that we don't need to talk about. Okay. But if you wanted to insist on putting units in here, then this too would say that the rate of change of the x coordinate is 2x units. Inches, feet, meters, whatever per unit time. Seconds, hours, whatever your units are.
Okay.
Yeah. Yes.
So what about the problem made us use
Oh, wait, it's not that we have to use the dot product, it's that we can use the dot product. So I'm choosing to use this formula right here, this sort of version of the chain rule. And now again, not that I have to, I could write this as a matrix times a vector. But I can instead choose to do this matrix product as a vector dot product. Well, it's just the same numbers. I mean, so just as a for example, if I have A, B, C, and I multiply by X, Y, Z, just to throw some numbers down, right? This matrix times that vector, the result is exactly the same as if I were to write the dot product of A, B, C as a vector dotted with X, Y, Z, the vector. So you just multiply them out. Both of these things are equal to AX plus BY plus CZ. It's just kind of a algebraic, I don't want to say coincidence exactly, but it's just, they're just the same exact expressions. Is that cool? Yeah. The fact that we have a single output variable here, the fact that it's just Y, one output variable is why there's only one row in this matrix, which is what allows this to be on the table.
Where's the one output variable?
So what we've got here is we've got a situation where the premise here is that we have just one output variable, Y.
That's like the example we did?
You're talking about this example down here?
Yeah.
Sure. So what we've got down here in this scenario is T is an input, bird position is then X, Y, Z, and then the eventual output variable is just the temperature, capital T. Right? So we have the one output variable, one input variable. We're computing the rate of change of that eventual output with respect to that initial input using the, again, chain rule, gradient, dot product, and all that.
So could we have used this dot product approach for the previous example?
No, we can't use it for this previous example because here in this example, notice that our function has multiple output variables, and our derivative, as a result, has multiple rows. And you can only interpret a matrix vector product as a vector dot product if your matrix only has a single row. So this is just not an option in this case.
I'm a little confused when you say multiple output variables. So what are the multiple output variables?
So
X1 and X2.
yeah, so here's our function. Our function f, right? Our function f takes two coordinates, x1 and x2, right? And it gives us three output variables. X1, or maybe we'll call them Y1, Y2, and Y3. Yeah.
Oh.
See what I'm saying? Yeah. Okay. All right. Okay, so those are, again, just special cases of the more general chain rule, and it's just kind of, I like to connect dots sometimes. Okay, different point of view now on the chain rule. Here's our chain rule again. The derivative of composition is the product of the individual derivative matrices. And again, if I've got, my first function here gives the y's as functions of the x's, then there's the derivative of that first function. The second function gives the z's as functions of the y's. So here's the derivative matrix for my second function. Again, the colors kind of seem to do a little switcheroo, so be careful. And then, of course, the composition gives me, for every collection of x's, I get a collection of z's, and here's the derivative matrix of that composition. So this is just a chain rule. What I've done here is written down the elements of these matrices that are needed to compute one individual element of the composition derivative. And if you notice, in order to compute that, I really only need to know this one row of this left matrix. And I really only need to know one column of this right matrix. And the dot product that I do to get that purple entry is, well, here's the green entries multiplied correspondingly by these blue entries, and there's that dot product. So this is that dot product. And if it should be the case, as it sometimes is, if you only need one specific entry of a derivative matrix, this is very often the case that you just, for whatever reason, you only need that one entry. You can just remember this one formula and not have to compute the entire matrix. You notice we didn't make any use in this example. We didn't use any of this junk down here or any of whatever it is up there. None of this got used. None of that got used. All that would have been a waste of time. Right? So this formula in purple down here allows us to kind of streamline the process a little bit. Now again, pros and cons. If you want to compute just that one entry. If you need to compute the entire matrix, you don't want to have to write this formula here down 9 times. Right? That would be less convenient. That would be by far clunkier than the matrix. The matrix does all the bookkeeping for us. It keeps things in order automatically for us. Very nice. So, right tool for the right job, and this is just another tool. Okay, now before we get to an example, I do want to give you a warning about this formula here. Some students will look at this part and say, hey, wait a second. Partial y1, can't I just cancel those? All right. And then look what I'm left over. I've got left over partial zi in the numerator, which is what I want, and partial xj in the denominator, which is what I want. There's a temptation to just stop it right there. Everybody see the allure of this? Pretty tempting. So, very important to recognize this is wrong. First observation I'll make is saying that this is all you need is simply incompatible with what we already know to be true. We already know this matrix form is true. This is what we justified in the first place. So, incompatible with a known fact, already bad, right? But let me explain what's wrong with the reasoning. This cancellation reasoning, right, just doesn't work. This presumes that what this means is the exact same as what that means, and it isn't. I have to apologize for the notation here. It's not my choice of notation, but the notation makes it look like we've got fractions of well-defined, independently existing objects. That's what the notation looks like. But we don't. These are not fractions of well-defined, independently existing objects. Each one of these is just part of a story. It's part of a scenario and certain roles being played in these different scenarios. So I want to walk through these two scenarios. Let's talk about what's the story here when I compute partial zi, partial y1. What does that mean? What's going on? What's happening there? Well, for one thing, we're taking a partial with respect to y1. Partials means that all my other input variables are constant. That means that all these y variables are constant in that story. When we're looking at that purple partial on the left, all of the other y variables have to be constant in that story. Okay, now let's compare that with what's going on over in this story. In this story, we're taking a partial with respect to xj. That means we're going to hold all of the other x variables constant. But with those x variables held constant, we're going to change xj. We're going to change one of the x's. And unavoidably, when you change one of the x's, all of the y's, you should assume, are also going to change. And so in particular, the y variables, let's see here, color choices. These y variables will not be constant. So these are totally incompatible scenarios. What's going on in this purple thing and what's going on in this orange thing, different stories, different scenarios. So this partial y1 is not only is it not the same thing, it's not even part of the same story as this partial y1. So it just makes absolutely no sense to cancel them. They're not the same thing. They're unrelated. It's like in the same way that if there's an X in number 2 on the exam, and if there's an X on number 5 on the exam, yeah, they're not the same. They're different questions. They're completely unrelated. I happen to use the same letter of the alphabet. They're not the same X. Does that make sense? I mean, that's sort of an obvious example there, but this is kind of the same sort of a deal. Yes?
So if instead of del, these were d's, does that change things?
Then I wouldn't be clear on what these things mean. I mean, if I were to say dzi, dy1, that would mean single variable derivative, and zi is not a single variable function, right? And so that's also not a thing, but for a different reason. I don't know, is that satisfying?
No, it's just that when we've done integration in the past, you change the variable with respect to which you do the integration, and then is it effectively you're canceling, or is that...
You're talking about like substitutions in single variable?
Is that a simplification of what's actually happening?
Well, it's a pretty different scenario. And substitutions is something that's, yeah, we're a little sloppy with that notation in math as well. It can all be cleaned up. It's perfectly fine. It's not a actual rigor problem. It's a notational awkwardness problem. In that case, with substitutions, it's perfectly fine. But it's perfectly fine for reasons that usually don't get talked about. This one just isn't perfectly fine, and so I'm trying to explain what the problem is. But yeah, this other scenario with substitutions, yeah, also weird. Just happens to be a weird one where there's no actual problem. Yeah. Anybody else? Is everybody good? Okay, so be real careful not to step on that landmine. Again, it used to be far more common than it is now. I've been hitting this point pretty hard in the last several years due to noticing a lot of students having this problem. Don't make the mistake of thinking that you can just write that down. It does not work. It's absolute nonsense, and it's not worth any partial credit either. So make sure to understand the chain rule kind of completely the right way there. Okay, now there is a nice interpretation of this formula. I think is really satisfying, but more to the point, it's really useful in applications. So we're going to take a certain point of view here, and that point of view will be applied into a bunch of applications. Here we go. The point of view says, if you want to understand this partial derivative, let's document the functions themselves on a diagram kind of like this, where I can see, the inputs and the outputs of f. I can see the inputs and the outputs of g. I can see them all right here on this diagram. And let's just annotate what happens when I compute this partial derivative. Here we go. Taking the partial derivative of zi. There's zi. We're taking its partial with respect to xj. Here's xj. Partial derivative means I'm holding all these other variables over here constant. Right, so all of those are constants. What happens when I change xj a little bit? Well, here's the thing. When you change xj, that change is going to cause a change in y1. Right? y1's a function of xj. Change that input, you're going to change that output. When you get a change in y1, that is going to cause a change in zi, because among other things, zi is a function of y1. Right? And furthermore, I can tell you sort of the magnification effect each step along the way here. However much change there is in xj, how much, by what factor is the change in y1 different from that? Well, the multiplicative factor, or input change to output change, is what a partial derivative is. So the factor of change along this orange arrow is partial of y1 with respect to xj, which you see right there. And the factor of change along this arrow from y1 to zi, well, that's, again, a partial derivative. It's partial of zi with respect to y1. So altogether, this term, think of that as coming from keeping track of how changes kind of propagate along this path. Here, let me do it like this. Changes propagate along this path from xj to zi. Yes?
Do you find like the path of doing like a limit definition of a derivative, like of another limit definition of a derivative?
One more. I'm sorry. Say again, please.
Like if you're trying to find the partial derivative of zi,
Yeah.
with respect to xj,
Yeah.
do you do the limit definition of the derivative, right? With the change being the.
If you want to be rigorous about it, then you'd have to worry about those things. But I'm going to some trouble to avoid getting rigorous about it. Yeah, that's not Math 219 isn't about the rigor. So I'm just trying to speak sort of intuitively here, right? And the idea is, intuitively speaking, a partial derivative is a relationship between input changes and output changes. So boom, right? And let's not get into the rigor that's more of a Math 222 thing.
But like, are we just saying that like it's like the value as zi plus the change in the value that we get from y1, and then we just subtract like zi as your like quote-unquote derivative, right?
I'm not entirely sure what you're asking, but when I say change, what I mean is that if there is an initial value, right, then there's all the subsequent variables have their values, but if you change the input a little bit, then everything else downstream changes also. And I'm just trying to compare how much xj changes with how much y1 changes, and then compare how much y1 changes with how much zi changes.
So can we say like the change in zi is based on the change in y1?
Yes.
Okay.
Does that make sense? Okay. Cool. Okay. So this term. Let's see here if I can. Here we go. Okay. So this term in this formula that we have up here that came from the matrix form of the chain rule, you can think of that as basically keeping track of how changes propagate along that path. And further notice, this path corresponds to this variable y1. It's the path in some sense goes by way of y1, which is what we call an intermediate variable. And then of course there's several other intermediate variables. There's also the y2 is an intermediate variable, and there is a y2 term in here that I didn't write down for lack of space. And there's a y3 path and a y3 term, et cetera, and then finally there is a ym path corresponding to the ym intermediate variable, and this is the ym term. So this is a way to think about this formula. You can think about it as coming out of the matrix form as a sort of a one element at a time, or you can think of it as just keeping track of all these different paths along which changes can propagate and writing down the corresponding term for each one. And this latter point of view is again going to be something that we're going to use a lot in applications. Okay, let's see an example of this. Here we go. We've got our function f that takes in x's and spits out y's. I've got it documented on my diagram there. There's the x inputs and there's the y outputs. And now I've got my second function g. Notice that the outputs from f are the inputs to g, as they should be if you're going to compose. And let's see here, then g takes the y's to these z's. So this part of the diagram here sort of is the g part of the diagram. So I've got my diagram. I've got this sort of, analogous to this picture up here. I've got my diagram for this pair of functions. And let's see what the question has asked us. The question asks to compute the partial of z2 with respect to x2. Okay, well, let's see here. z2 is right there. x2 is right here. And what paths are there between x2 and z2? Said differently, what intermediate variables are there? And, well, the only intermediate variables are y1 and y2. So there is a what you might call a y1 path and thus a y1 term. There is a y2 path and thus a y2 term. How are we doing? Everybody follow all that? Okay. Okay. Okay, so now, and then of course there's some algebra I've got to actually crank out what these partial derivatives are. And this is just, tedium, y'all know how to take partials. Notice that Z2, for example, is Y1 cubed. So if you want to take the partial of Z2, well, it's, you follow the rules. Partial of Z2, partial of this with respect to Y1, 3Y1 squared. Everybody okay? Yeah. All right. All right. So a couple of heads ups. First one, don't commit confusion of variables. I'm going to show you a confusion of variables in a single variable context. We try to go through really quickly through this, just because it is all single variable. But if someone were to give you these two functions and ask you to compose them and take a derivative, well, we know the composition is x to the sixth. We know the answer needs to be 6x to the fifth. Casual observation, right? But if you are a little too casual with your chain rule, and you just write down, well, here's the derivative of g, and here's the derivative of f, and you just kind of write them down, notice you get a wrong answer. Okay. You can avoid that by remembering that g prime has to be evaluated at, not at x, but at f of x. Right? We talked about that last time in the multivariable version anyway, and of course this is an old formula from single variable. So g prime is 3 times something squared, sure, but it's not x, it's f of x, and of course f of x is x squared. Right, so you got to plug in the first function into the second derivative. And honestly, that's pretty confusing, right? We've got x squareds being plugged in where x used to be. That's weird and awkward. So you'll notice, even though we do get the right answer here, and I call it valid, it's still confusing, and I think suboptimal. Let me show you what I think is the much more natural way to do one of these, and that is to just recognize that, look, when you compose two functions, you're doing a composition, you got to think about what variables are we going to put in what places to keep track of what's happening. And, well, if f is written in terms of x, as it is here, what am I going to call the output from f? I can't call it x. Right? You can't have x being both the input and the output for the same function. That's definitely a confusion of variables. So I can't call it x, I guess I'll call it y. That kind of forces my hand then, though. What am I going to write g in terms of? I have to write it now in terms of y, because what comes out of f has to go into y. So I need to rewrite this function g in terms of y. And I emphasize, I haven't really done anything actually substantial here. G is the function that takes whatever you give me and it cubes it. I've rewritten it now in terms of y, the punchline being that g is the function that whatever you give me, this cubes it. It's the exact same function. But I've written it in terms of a different dummy variable. And so it looks a little different. It's the same exact function. But having written it this way, I have avoided my confusion of variables problem, and now look how easy the derivative is. It's just a matter of, okay, there's your chain rule, be as sloppy as alike. Derivative of composition, product of the derivatives. I'm not even going to worry about where we're evaluating it. The notation's going to keep track of that for me. G prime, 3y squared. Fine. F prime, 2x. Fine. Whatever. Multiply those, fine, 6y squared x. Oh, wait a second. The composition is a function of x. I need my answer to be a function of x. I need, therefore, to figure out how to rewrite y in terms of x. And y is just the output value for f. It's x squared. So, again, the notation has kept track for me of what I need to plug in where, and you plug it in, and out comes the correct answer. And so I think the most elegant and risk-free of the different approaches that you can take on this problem. So, nice short punchline. Don't confuse your variables. Right? Okay, now again, that was all single variable. Y'all know single variable, but the same exact problem comes up with multivariable. And you can have a perfectly good function called f, perfectly good function called g, both written in terms of x and y. Not immediately a problem, so it would seem, right up until the point where you compose them. And when you compose them, then we've got this same exact problem. Look, whatever are the inputs to f, they can't be the outputs from f. The outputs from f need to be a different set of variables. Let's call them u and v. Well, that means g is going to have to be written in terms of u and v, and that turns this formula for g into that formula for g. Same g. I didn't do anything to g. I just wrote it in terms of different dummy variables. Right? And having made that switch, having avoided my confusion of variables now, I can take the derivative willy-nilly, not even worrying about where I'm evaluating what. You just find the derivative matrices and you multiply them. In the proper order, of course. And having multiplied them, and again, we find ourselves in this scenario where I've got this, I'm looking at this thing, u. I need my answer to be in terms of x and y. X and y. How am I going to write u in terms of x and y? Well, u is the first output variable from f. So it's x squared plus y squared. And I just plug in accordingly. Everybody okay? Alrighty. So next thing, another potential problem. You gotta make sure that when you draw these diagrams, and let me go back up here to where we were, diagrams like the one we were just working with, your diagrams have to be representative of an actual composition of functions. If we're going to apply the chain rule, our chain rule, as we understand it, only applies if you are composing, which is a very precisely defined thing, functions, which are very precisely defined things. Right? So every time that we compose functions, yes, I can draw a diagram. It is not, however, the case that any time you can draw a diagram that this necessarily represents an actual composition of actual, strictly speaking, functions. Right? So notice in this first example I've got over here, here's my what I'm going to call my f functions. I've got inputs, I've got outputs. Here's my g function. There's my inputs, there's my outputs. Perfectly unambiguous, no questions about what goes in, what comes out. And then, notice further, what comes out of f is exactly the same set of variables as what goes in to g. So that's what a composition is. So this is all fine. There's nothing wrong with this diagram. I can totally work this diagram. It actually represents a composition of functions. Cool. What's going on here? This is a mess. Where is the function? And is this actually a composition, strictly speaking? I mean, here's what I think might be the closest shot you might consider. You might think of this going to there as being the first function. The x's are the ins, the y's are the outs. But then maybe you want to think of these as being your eventual outputs, but notice Z1 and Z2 are not just functions of y1 and y2. Z1, for example, is a function of x1, y1, and y2. So the variables that go out of the first function are not exactly the same list as the variables that go in to the second function. I don't know what this is. It's not a composition of functions as we've got it written here. Does that make sense to everybody? So don't feel like you can just kind of go willy-nilly. And now you might find yourself in a circumstance where this looks like the right diagram to draw. Let's look at this set of equations right here. That set of equations. y1 is a function of x1 and x2. Y2 is a function of x1 and x2. Let's see here. Z1 is a function of x1, y1, and y2. And Z2 is a function of y1 and y2. So, I mean, this is kind of the diagram that you would think you should write down when you see this list of equations here. But it's not a composition of functions. You cannot work with this as it is. We're going to have to figure out some way to actually make sense out of what's going on here. Let me point out, before I get into the rest of this example, let me point out another real awkwardness about what I've got written here. Let's ask the question, what does this partial derivative mean? What's the partial of z1 with respect to x1? Well, if I view z1 as being a function of these three variables, as seems to be indicated there, I guess it would mean that I'm going to view x1 as my variable. I guess because it's a partial derivative, that would mean that I have to hold y1 and y2 constant. But that's not even possible. Right? If x1 is changing, x1 is a variable, y1 and y2 are going to change because they're functions of x1. So I don't even know what this means. Everybody see the problem? This is a mess, right? So you can't do something like that. What you've got to do is figure out a way to fix it. And there is a nice, easy way to fix it that I have down here. This is what I'm going to call the fixed diagram. And notice all I really did is I took this line, the dependence of z1 on x1, I kind of inserted a new variable in here called x1 star. That really, honestly, x1 star, it's just x1. But I want to view it as being a separate variable so that it can be the input to z1 without also being an input to y1 and y2. I'm kind of breaking up the awkwardness of that line by just introducing a new variable called x1 star. And again, the formula for x1 star is just exactly x1. But now, check it out. Got a perfectly good function right there. Got a perfectly good function right here. Notice that the outputs from the first one are exactly the same list as the inputs to the second one. And we're in business. Right, this is perfectly fine, not a problem. And then all I have to do is rewrite everything accordingly. In particular, z1, previously a function of x1, y1, and y2, now no longer. Now it's a function of x1 star, y1, and y2. Now it's the same formula, right? x1 star is x1. We have the same thing. I didn't do anything. Nothing really happened except now it's phrased as an actual legal composition to which I can apply the chain rule that I've developed for compositions of functions, and we're safe. And it's all downhill from here. So we've got here then our four equations. We've got a diagram representing the functions that that are relating in these equations. And let's see, I want to compute, it seems, partial of z1 with respect to x1. Okay, well, z1 is there. X1 is here. And I've got three different paths, thus giving me three different terms. Notice that one of these has a factor, which is partial of x1 star with respect to x1. That's kind of that leg, if you will. And what is that partial of x1 star with respect to x1? Well, it's x1 star is x1, so that partial is just 1. And so that factor just drops. Just a factor of 1. And there you go. There's you can do whatever else is necessary. Compute all these individual partials with those green equations, and we're like I say, we're in business. Is everybody okay? So just heads up, try to avoid meaningless garbage. It's going to get a lot of not only wrong answers, but nonsensical reasoning, and that's not a good thing. Okay. All right, so we're kind of out of time, so we'll draw the line right there for today. Quick reminder, exam on Friday. I'll be sending out an email about logistics probably tomorrow morning. Not that much to say other than, be on time. The exam starts pretty much on time, probably a couple of minutes after class time starts. Right here in the same room, normal time and everything, 50 minutes. Bring a black pen. Black pen is a requirement. That's because of how we do scanning. It has to be written in black pen. Email to follow tomorrow morning. See y'all later. Have a good one.